Let's look at Chapter 12 of Pagano's Understanding Statistics. Now, the goal of this chapter is to get you to be able to do a Z-test, or sometimes called a Normal Deviate Test. Now, this is our first regular inferential statistics test that we'll be using, the type that we would use in real life. And so we're going to kind of go slow and look at some of the concepts underlying it. They're fairly complicated, and this is the point in statistics where a lot of people get lost. Now, if you don't understand all of the vocabulary or the logic, you'll still be able to do the tests and use the stats calculators and things like that, but try to understand some of these concepts to see where these equations are coming from. Let's start off with a short quiz to review. So you remember Beep Beep, he's the bear. I think he's back there. Yep, he's back there. And he believes that he can influence coins when he eats cookies so that they land heads more often than tails. He claims to have cookie power. And we want to test to see if that's really true, if he can make coins land head up. So his null hypothesis is that the coins land heads 50% of the time or less. So his hypothesis is he can make them land heads more than 50% of the time. So the null hypothesis is the exact opposite. Now, if he wants to be 95% sure he's correct, if he rejects the null hypothesis, what's his alpha level? Think about that. And you're probably thinking, oh, his alpha level is 0.05 or 5%. That's correct. That means that 95% of the time, if he rejects the null hypothesis, he'll be correct, and there's about a 5% chance that he'll be off. We call that type 1 error or alpha error. Okay, now let's use some example with pennies. You guys know that pennies all have dates on them. And it turns out that the average penny in circulation that's sitting around in your pocket is about 16 years old with a standard deviation of 5. And that's about the average. If you have some samples, it'll be more than 16, some will be less than 16, but on the average, the coins are probably an average of 16 years old in your pocket. Suppose we take a sample of n coins, say 30 coins or so, and we calculate the average of that sample. That would be the sample mean. And so it might be higher than 16, it might be lower than 16. Now, let me ask you, if we take lots of these samples, if we had everybody bring all the pennies that they have sitting at home, and each person calculated the average, what do you think the mean of all these X bars, of all these averages would be? We call this mu sub X bar, or the mean of the sampling distribution of the mean. This is a weird concept. It's an average of averages, or a mean of means. So we call that mu X bar in the textbook. So what do you think the average would be of all of these? Well, if you guessed 16 years old, you would be right, because the average penny is 16 years old. So if we take a bunch of averages, we would get 16.1 again. The next question is, what would be the standard deviation of all these means? Would it be 15 years like it was for the individual penny? Or would it be reduced? Would the older pennies cancel out the newer pennies, and even though the average would still be the same, would the samples have a less variety of average ages than individual coins would be? You might think, oh, that seems logical. And if that's correct, it would be. Rather than having a standard deviation of 15 years, these averages of all these averages turn out to have an average of the standard deviation divided by the square root of the sample size. So if we all brought in 30 pennies and we had a sample of 30 pennies, and even though the pennies would have a standard deviation of 15 years, our samples would be much, much closer to each other. The standard deviation of our sample averages would be 15 divided by the square root of 30, and that would equal 2.7 years. So most of the averages would be like between 13 and 19 years old. Whereas the pennies go all over the place, from most are between 1 and 31 years old, the averages would be a lot closer. Now, let's say if you suppose you had a penny that was 25 years old, so something like from the early 1990s, late 1980s, something like that. Could you say, oh, that's not a normal penny? That doesn't come from the regular pennies that are in circulation. Or would you say, oh, yeah, that's not too far away from the mean, especially given that we have a standard deviation of 15? Well, if we had a penny that was 25 years old and we asked, could you tell if it was different from a different if it came from a different population than the population in question, rather than being just a coin in circulation? Is this something that probably was stolen from someone's coin collection? Well, the mean age in circulation is 16 and the standard deviation is 15. Let's calculate the Z-score to see how unusual it is to get a penny that's 25 years old. Well, first thing that we do to calculate a Z-score is we take the age of the penny that's in question, subtract the mean from it. That'd be 25 minus 16. And then we divide that by the standard deviation, which is 15, and we get a Z-score of minus 1.6. Ooh, a Z-score of minus 1.6. That's nothing unusual at all. So we would retain the null hypothesis that this penny came from just out of circulation regularly. So it's quite likely that it's very likely that it could very well be from the population of coins that are in circulation. Now, suppose instead of having just one penny that was 25 years old, we had a sample of pennies where the average age was 25 years old. So it wasn't like the coins that we have that were on an average 16 years old, but the average of these 30 was 25 years old. And we're going to call this the X bar obtained from the sample. Could you tell if it came from a different population from the population in question? So one penny that's 25 years old doesn't seem any unusual, but how if we had 30 pennies that were on the average 25 years old? For this question, we're going to do a z-test. We're not going to calculate the score for just one penny. We're going to do a test on the sample. So the average age of the penny was 16, and the average of the averages, mu x bar, was also 16. The standard deviation of the individual pennies was 15 years, but the standard deviation of the sampling distribution of the means, that's the standard deviation of all the averages, was that formula sigma divided by the square root of n, which in this case, 15 divided by the square root of 30 would be 2.7. So in the z-test, what we do is we calculate a z not on an individual penny, but on the sample. So we're going to use the same formula using this formula for the standard deviation. So it's going to be the average of the sample minus the population average of all of the means, divided by this new standard deviation, which is the standard deviation of the dates, divided by the square root of n. We pop that into a calculator, and we get minus 3.3. That's more than 3 standard deviations below the mean of what we would expect for a sample of 30 coins. This is an extremely low z-statistic. We're going to reject the null hypothesis. We're going to say, oh, we found strong evidence for our hypothesis that these pennies came from somewhere else, like a coin collection someplace. So this is an example of the normal deviate test, or sometimes called the z-test. It's a test to see if a sample is different from a given population. Did this sample that we have come from the population, or is it from something different? Is it a different nature than the population? We calculate a z-statistic, and that's called z-obtained in the textbook, for the sample, not for an individual score, to calculate the probability of getting a sample with that mean from the population. And so this z obtained This Z statistic is calculated from the mean of the means and the standard deviation of the means, which is the standard deviation of the individual coins, divided by the square root of n. So if the probability is low, that means we have a high Z-score. We say that the sample is not likely to have come from the same population. We reject the null hypothesis, and we find evidence for our main hypothesis. Now let's look at an easy to understand sample. Suppose you go to a church that has a large college-age group. Now, I teach at Azusa Pacific, and lots of people at Azusa Pacific are committed to Christ and go to a youth group, and they study the Bible with other people their age and do a lot of service activities. They might have some fun activities too, and they just do a lot of things together. So this college group that we're imagining has an average attendance of 100 with a standard deviation of 10. So usually there's between like 90 and 110 people. They have a big outreach activity to attract new people to the group at the end of April. In May, they start measuring the attendance, and it's 105. Specifically, it's 100, 105, 95, and 120 for those 4 Sundays in May. So they've gotten a sample of how the group might have changed. Now the question is, does that really indicate that the group has grown? Or could we say, so that our hypothesis is going to be the group has grown. Our null hypothesis is that our group hasn't grown, and it's not unreasonable to expect a group with an average of 100 and a standard deviation of 10 to have an average of 105 for 4 Sundays. So we specifically want to be 95% sure that the group has grown in May. Now, this is interesting because you might be saying, well, why would a college group want to grow? Why not just let everybody do what they want to do? Well, it turns out that one of the things that Jesus commanded was that he wanted people to know him personally. And one of the last commandments that he gave before leaving the earth was go and make disciples out of all the nations. And so as Christians, people that are truly committed to Jesus Christ, not just people who call themselves Christians, but ones who are real Christ followers, they do things like outreach in order to do evangelism. And evangelism is a word that means to good news somebody, share some good news with them. And the good news is what the New Testament is all about, the Evangel, the Injil, the gospel. It's this idea that Jesus came and died for us so that we could have our sins forgiven and be reconciled to God and be transformed and live in a community that loves for one another. And this evangelism should lead to discipleship, people that are personally committed to following Jesus, to being his disciples, and living in love towards God and towards other people like Jesus commanded us to. So that's the goal of why a church group would want to grow, is that other people can experience God in the same way that they have also. Now, how would we test this? In the college group example, the first thing that we should do is define the alternate and the null hypotheses. So H1, the alternate hypothesis, or our main hypothesis, is going to be the college group has changed size. So this is a non-directional, two-tailed test. So that would be one hypothesis we have. We could have the hypothesis that the college group has grown. So we could choose either one depending on which we're interested in. Now, suppose we want to know if that outreach activity was a disaster too, so we'd want to test for both changes in both directions. Now, the null hypothesis would be the opposite of this, is that the college group has remained at the same size. That is, the size after equals the size before, and there hasn't been a change. And so this null hypothesis, that nothing's happened, will be retained if it's reasonable to consider that a sample of just these 4 scores with an average of 105 could easily occur if we were still dealing with a population that had the average size of 100 and standard deviation of 10, i.e., there had been no change. So if it's reasonable to think we could have gotten an average of 105 for 4 Sundays, then we're not going to claim that it's grown. Now, the second step is to calculate the statistic that we need. Now here on this PowerPoint, I'm going to calculate it kind of manually. However, when this video is over, there's going to be a video on using using Excel, and specifically using a ZScore calculator that you could either find online, or I'm providing an Excel version of one in the link to that video. And you don't have to worry about getting the Excel command exact, because it's actually pretty complicated. But looking at how we would manually find the Z obtained for the Z test, we're going to use the equation Z obtained is the X bar obtained from the sample, which would be 105 in this case. Mu is the population average, was what the average of the group was before the outreach activity. That was 100. And we're going to divide that by our mini standard deviations, the standard deviation of the attendance on the Sundays, which was 10, and we're going to divide that by the square root of the sample size, which is 4, because we had 4 Sundays. Now we put that all together, and we get a Z of 1.0. Ooh, it doesn't sound very big. Well, what we need to do is to find out, ooh, is that big enough? And so what we need to do is we need to find the probability of obtaining that statistic, that Z obtained equals 1.0, if the null hypothesis is true. And we're going to reject the null hypothesis if the probability is too low. If it's too freaky, like, oh, no way could we have gotten that low of a Z-score, we would reject the null hypothesis. However, if it's not too freaky, if it's not unusual, we're going to say, oh yeah, I guess we could have gotten that by chance. So in our example, Z obtained equals 1.00. We want to find the probability of getting the results this extreme or more extreme in either direction. So we want to find the area under the two tails. Now, using Excel, we could remember that norm S dist formula that we looked at when we calculated Z-scores. We could use that, and in fact, the Z-score calculator that I'm going to give you does use this. The area to the left of Z obtained equals 1 is going to be 1 minus the norm S distribution of 1, because we're looking at the area to the left, and the norm S distribution usually gives us the area of the right. The area to the left, it turns out, we call this the p-value, is 0.1587 from using this formula here. Now it's two-tailed, so we need to add both tails, and so the two tails are symmetrical, so we add 0.1587 together, and that equals 0.3174. So there's a 32% chance of getting the statistic this extreme if the group really hadn't grown. That's pretty high. In fact, this is greater than our alpha equals 0.05, so we have to retain the null hypothesis. We say, maybe the group has grown, maybe it hasn't grown, we don't know. That's what retaining the null hypothesis means. We conclude that the college group might not actually have grown. It might have grown, but we don't have enough evidence to really conclude that. So there's a 32% chance that we would have attained these results, or a result this extreme, by chance if the null hypothesis were true. Now that's how you would manually calculate the Z statistic for the Z test. In the Excel program that you're going to look at in the next video, all of this is done automatically for you, and that makes it easier. So you can use the Z-score calculator that I'm providing for you, or you can just Google Z-score calculator and you'll find plenty of them online.